Good afternoon, everyone. Welcome to the BNI Learn at Lunch series. The title of today's presentation is Forecaster, Accessible Time Series Predictions. We have a few announcements before we get started. I wanted to remind everyone about the CCTS Spring Conference. It will be at the Central Bank Center on Tuesday, March the 31st. The theme of this year's conference is AI, Bridging Clinical Care, Innovation, Research, and Technology. Please be sure to pre-register by March the 26th. You can visit our website to do that, and we're looking forward to seeing you at this year's conference. We have a couple of really great outside speakers talking about things going on in AI, so I think it'll be a great learning experience for all of us. Following today's presentation, you will receive an evaluation via email. We encourage you to complete the evaluations. The CCTS provides certificates of attendance for anyone that would like one for their records. As a reminder, you must be present for the speaker's entire presentation to receive a certificate of attendance, and a link for the certificate will be located at the bottom of the evaluation. The objectives of today's presentation were included in the presentation invite, and today's speaker has no disclosures to make. Today's speaker is Aaron Mullins. Aaron is a software developer at the Center for Applied AI. He began his work with the group as an undergraduate intern and now holds a graduate degree in data science. His expertise includes machine learning, data analysis and visualization, and working on projects leveraging classification and time series forecasting. Please join me in welcoming Aaron Mullins.
Hi, thank you so much for the introduction, and thank you everyone for joining. Today I'm going to be talking through kind of time series forecasting a bit as a field, and then talking through a specific tool that we have developed at CAAI called the Forecaster that's meant for kind of making these time series forecasting methods and techniques more accessible to researchers and clinicians. So just to make sure we're all on the same page at the start about what problem exactly this is trying to solve. Time series forecasting is the process of taking any kind of data over time where consistent measurements are made or taken at different intervals, and you want to use that data to predict what the values will be at a future time. And this has uses in a lot of different domains, but especially healthcare at both like a population level, such as, forecasting the number of COVID cases that a certain region would have in a given month, as well as kind of at an individual level, like monitoring patients in the ICU, looking at their vital signs and trying to forecast, whether they'll get better or worse over the next couple of hours. So there's a lot of different ways that you can perform a lot of these techniques, some of which are more statistical models, some are more kind of machine learning focused, and I'll talk a bit more about specific models later. Um, but the important thing is that these techniques that you can implement are very powerful and have a lot of different uses, but they can be difficult to implement, especially for researchers who want to use these techniques and the results that they can produce without having necessarily the technical background required to like write code to actually build and train a model, and then evaluate it. And so at CAI, we figure that making these methods more accessible to researchers can lead to a lot better health outcomes with whatever problem they're trying to solve with their data. And there's a couple different techniques out there right now that are typically used for forecasting, and they each kind of have their own pros and cons. And at one end of the spectrum is Python. There's a lot of different packages to Python that are built specifically for time series forecasting. They're very customizable and they're very powerful. They're able to be implemented in with kind of any kind of data and modified however you need. But of course, the cons here are that it's if you don't have a coding background and don't know how to write in Python, then obviously you can't really use these techniques. And even if you do have a Python background, they can still be very difficult to optimally implement because they are so customizable, because there's so many different parameters and options you can choose between. It can be really overwhelming kind of to determine what you're supposed to do to best apply it to your use case. On the other end of the spectrum is a platform like Excel. Probably everybody here uses Excel at some point in their work. And so it's very approachable. It's not technical. It's very commonly used, but it is much more limited in the capabilities for forecasting. There are certain functions that you can run to generate kind of simple linear forecasts based on your data, but it's very rigid. It's not customizable, and it's not very powerful for any advanced techniques. And then you have your commercial solutions. These are things like Google Cloud, AWS, DataRobot. They all have very powerful forecasting techniques integrated within them, and they are kind of built within a lot of existing platforms like Google and Amazon, where a lot of data is already stored, which can make that process easy. Obviously, the con with these solutions is that they are prohibitively expensive most of the time. They're kind of built more for like a business overall to implement rather than like an individual researcher wanting to explore some kind of research question. And they can still be pretty difficult to learn, even if they aren't really as technical as something like Python. They can have a very steep learning curve. And so we wanted to address kind of this gap in the ability to implement forecasting models with different kinds of data. And so we built a platform called the Forecaster. And a couple of the main features of this are one, that it is open source. So we have code available for downloading and for like running any local instances of this platform if that was something that you were interested in. But it runs primarily on a web-based interface, and so it does not require learning any kind of new platform or coding language because you can just pull up this website and click through some pages to use it. And so what exactly does it do when you go on the website? Well, it incorporates a lot of different steps to the forecasting process, including data pre-processing. I'll talk more about what that involves. Actually training the models themselves. So choosing, a model from a drop down, and it actually will just run the training on that model on the back end and then produce results that you can look at and different evaluations for those results to indicate how well your model is performing on your data. There's visualizations to make it a lot more explainable and easy to understand, which I will showcase some examples of later. And then there's also a system for LLM recommendations because some of the parameter choices or result metrics can be kind of confusing or hard to tell the difference between. And so we wanted to provide some automated assistance to explain the differences between certain options that you might have on the website. And so I want to start with the idea of data pre-processing. And while I'm kind of going to frame this from the perspective of what a forecaster can do, these are kind of important steps that you need to do for any kind of time series forecasting. Because as you'll see, depending on the type of data that you have, you'll need to kind of define how your data is supposed to be used by the model that you're training. And so this is something that you can do through the web interface, which I will show an example of. But essentially what it means is if you imagine that you have a CSV file or an Excel file, and you have all your time steps, in one column, and then you have other columns with other kinds of data. You want to be able to explain how each of those columns is supposed to be used in the final model. And so Forecaster kind of lets you define a role for each column, and there's 6 different roles, which I'll give examples of here with a data set to give a better picture of what each of these roles actually means. And so, like I said, this is important for Forecaster, but it's also important just in general with machine learning to best understand kind of how different types of data can be used by these types of models. And so let's say that we have a data set here that tracks COVID-19 cases throughout 2020. And as you can see, we have six different columns here. And I'm going to walk through each one and kind of talk about how they can be used within the forecasting process. And so we'll start here on the left side. You can see we have a location column. So we have several different countries that we want to make predictions for. So in this example, we have the US and Turkey, but you can imagine that we might have a bunch of other countries. And we want to make predictions for all of those at the same time in this example. And so, the naive way to do that might be to build a separate model for each country. And that would be one option. But the disadvantage of that is that a lot of these newer models can actually take in all of these regions at once and kind of learn the overall trends across them while still being able to adjust the individual predictions that it makes to account for any local differences. And you might imagine too that some regions' trends might precede the trends of other regions, and so they could actually hold some predictive value as well. And so, allowing the model to look at all of this data at once, make sure that it can capture those broader trends as well. And so in this case, we have our location, that's our grouping column. Not every data set is going to have one. We might only want to predict values for the US, and that's totally fine. But in the case that we have, multiple regions, like they can be countries, they could be counties of Kentucky. They don't even have to be geographical regions. If, for example, from like a sales perspective, if you had a store and you were forecasting sales, you could have different product categories, and each of those would be a separate grouping that you want to individually forecast as well. So that's something to keep in mind that that is an option for running these models where you can learn these broader trends across multiple different groupings. Then we have our date column. This one's fairly self-explanatory. This is indicating the time period that all of our measurements are from. In this case, you can see from looking at the column that it's daily. It increases by 1 day at each step. Not every data set will be like that. Sometimes it might be hourly or monthly or yearly, and all of that is possible to still work with. The important thing is that it's consistent. We're not jumping around between different days. We're not skipping, long periods of time at a time. We have kind of these consistent measurements. And so this is our time component. This is indicating to the model, how the time is progressing from time step to time step. And a lot of these models have kind of inherent things built in where they can take advantage of differences between months or a day or a week or things like that that might have an impact on your results. And it's important too that our time periods overlap across our different groupings that we established. So if we had our data from Turkey and it was a completely different time period than our data from the US, we wouldn't really be able to train them both with the same model. We would have to separate them. And so in this case, our time series overlaps. Then we have kind of the most important column, which is what we're actually trying to predict. This is, what we call the target variable. This is the thing that we want to produce forecasts for into the future. So in this example, it's the number of new cases each day for COVID. And you can have more than one different variable, and most models will be able to, again, look at multiple different variables at once and be able to make individual predictions for each of them. So if we wanted to predict like new cases and new deaths at the same time, we would be able to do that with one model. But in this case, let's say we only have this one target variable. And then we have a couple extra columns here, and these are kind of additional data sources that we want to use to help the model be more accurate with its predictions. Those are called covariates, and they are just additional data sources that might be kind of related to our target variable in some way. And so we want to try to see if we can provide that data to the model to make the predictions more accurate. So in this case, we have a column for the number of new tests that have been administered for COVID. We would probably expect that the number of tests administered in a given day is probably correlated in some way with the number of positive cases. And so this could be a very useful variable to include here. Now, there's a couple different types of covariates, which you saw on the initial slide for this section. And this one is what we would call a past covariate. And that means that we don't really know what the future values are going to be. So let's say that we had data up until this current time step today, and we wanted to make our prediction for the number of new cases tomorrow. Um, we don't know for sure how many new tests are going to be administered tomorrow at this point, right? And so that makes it what we call a past covariate because we don't know the value of this variable during the window that we're actually trying to predict for. Doesn't mean it can't be useful. We can still look at all the past trends. Things can be predictive several time steps into the future. And so it's still a variable that we want to include here to kind of capture trends that could be hidden or not identified otherwise. Another type of covariate is the future covariate. This is one that we do know the value for into the future during the period that we want to make our predictions for. So in this case, we have the season, and you can expect that, okay, maybe the number of COVID cases could be influenced by what season it is. So back to our example, if we wanted to make our prediction for tomorrow, we know what season it is tomorrow. We know it's still going to be winter. And so we can use that to make that prediction essentially a little bit more accurate because maybe during the winter we expect more cases or something like that. And so we can use that future value to help with our predictions. Hopefully, the difference between those two is clear and how we understand one into the future, but not the other. And the last type of variable I'm going to talk about is a static covariate, which is one that does not change in any significant way over time. So in this case, we have the proportion of the population of each country that is aged 65 or older. Obviously, this variable might change slightly from day to day, but not in a really significant way. And so the main value of this variable is it helps to kind of distinguish between different countries because perhaps the proportion of people age 65 or older is going to have some impact on the number of new cases that we want to predict. So this is really only useful if we have separate groupings we wanted to predict for. If we were only looking at the US, just knowing this value wouldn't be really useful again because it's not changing over time. But because we have multiple countries, we can use this variable to make distinctions between our different regions. So that kind of summarizes the types of pre-processing that you want to think about before you try to implement any time series forecasting models. Just thinking through, for your specific use case, what is it you're trying to forecast? Do you have different groupings you want to make predictions for, or multiple variables? And is there any other additional data sources you can include to help your model? And how can you use those realistically? I want to pivot now to talking more about the models themselves. So there's a lot of different techniques to performing time series forecasting. For the forecaster, we used a library called Darts in Python, which makes, implementing and evaluating these models fairly straightforward. And it's a library that you can use as well in your own code if you are a researcher that wants to be able to implement these models yourself. But the basic process and the way that these models work is you read in the data, you define your target, your time component, all your covariates and everything like that. And then the forecaster will iterate through every model that you select on the web page, which I will showcase in a demo here at the end. And it will kind of train and evaluate each one individually. There's a couple different methods for training that I will talk about in a bit. And then you calculate your performance metrics, which measure how well your model is doing and how well it's able to make its predictions. In the forecaster, there's 8 unique models, plus a very simple baseline that does like a very simple algorithm to make its predictions. And that's done kind of for a comparison to the other models. So you can see, well, if your model is worse than your baseline, then you know that model's not very good for your data set. And I want to kind of touch on each of these types of models, starting with the most simple and kind of building up to the most complex, to showcase just the variety of different ways that you can do time series forecasting and different techniques that you can try if you were to try to implement these. And so we'll start with linear regression, which is the simplest. It essentially plots all of your data points across different time periods and tries to find the linear relationships that can explain the trends. And so the That's the relationships between, past values of your target series, as well as any additional covariates that you've included. It it's not necessarily as good with very complex dynamics, but it can capture more simple relationships very effectively and can be a very good starting point for doing forecasting. The next one is exponential smoothing, which is similar to linear regression, with one kind of big difference that it uses a weighted average to favor your more recent data more heavily. So linear regression, more or less kind of treats all the data points in your time series as having roughly the same weight and impact on your predictions. Um, with some time series, maybe the just the last few time steps are really the most important and the most indicative of what your future value might be. Then exponential smoothing kind of covers that by weighing those most recent data points a lot more heavily, so they have a lot more impact in the prediction that gets made. And it does this by predicting kind of individual components of your time series. So every time series essentially has three primary types of components. The first being the trend. So this is just the overall direction of your time series. Is it increasing over time? Is it decreasing over time? Is it roughly, staying the same? Then the seasonality kind of captures any repeating patterns. So if you imagine we have, flu cases data, and we have flu cases across multiple different years, we would probably expect a repeating yearly pattern where you get a lot more flu cases in, the fall and winter, and then the number decreases in the spring and summer. So that would be your seasonality. It's your repeating pattern that you consistently see. And then there's always going to be error, which is the more unexplained. It's the variations from time step to time step, because not every time series is perfect and they're not going to perfectly follow these trends and patterns. Sometimes you hope that these errors can be accounted for by including additional variables, but sometimes they can't as well. And exponential smoothing itself can't use any external variables. It just kind of uses the target series itself. So that's the only model that isn't able to do that. And then the last of these more statistical based models is ARIMA. This is a very popular forecasting model because it works very well. It kind of analyzes the correlation of the target series to itself and uses kind of all the forecasting errors to improve the predictions as it kind of runs through the time series. It also, the I in ARIMA stands for integrated, which essentially means it's going to convert the time series into a stationary series, which just means that if your time series has very changing like mean or variance over time, then a lot of like statistical assumptions that these models rely on aren't necessarily true. And so it kind of adjusts the series to make it a bit more consistent and then kind of unadjusts it after at the end once the predictions are made to re-account for that. Then I want to move into the more machine learning based models, and that's starting with tree-based models. Essentially, what that means is that these models rely on kind of decision trees, which are basically flowcharts. So it is kind of a series of points that are connected through different conditions, and it takes, your data, it builds these decision trees to kind of optimally maximize your performance. And at the end, it kind of produces an estimate for what your forecast would be for a certain time period. And so a random forest is kind of the simplest example where it just builds a bunch of these different decision trees, and each tree uses different subsets of data, different covariates, different time steps, things like that. And it averages your predictions across all of those trees. The important thing is that each of these trees is like independent from each other. They don't rely on each other in any way. You just average all their predictions at the end. This is different from gradient boosting, which builds each of your decision trees sequentially rather than all at once, kind of independently. And so each tree that you build is basically built to correct the error in the previous tree's predictions. So as you build more and more trees, it gets more and more accurate and gets kind of better at forecasting your specific data. And then light gradient boosting is just another modification on kind of the same architecture that uses a different growth strategy for each tree. So the previous two methods use what's called level-wise growth, which means that the decision tree is grown one complete layer at a time. So you get your first node, then you build all your second nodes, then all your third nodes, all your fourth nodes, and so on. And that creates a very balanced tree versus a leaf-wise growth, which looks at the single kind of leaf or node at each point that reduces your error the most, which can create very imbalanced trees, but it works a lot better with like very big data sets and can run a lot faster as well. But if your data set is small, you don't have a lot of time points, then level-wise typically works a bit better. And finally, getting into the most complex deep learning models, we start with NLinear, which is a long-term time series forecasting neural network. So you've probably heard of neural networks as kind of a more complex architecture for machine learning. Some of these neural networks are built specifically for time series forecasting, and they're able to kind of take in data at different points to learn the trends across them. As far as neural networks go, this is actually a very simple model. It's just more complex than the previous ones that I talked about. Whereas the final model here, the temporal fusion transformer, this is the most complex model that the forecaster includes. Transformers use what are called attention mechanisms to basically relate every single time point with every other one. This is also how like LLMs learn how sentences are structured by comparing each word in the sentence to each other word. You can think of kind of a sentence as basically a time series, and it works in the same way. And so these Cook's models work very well with big data sets, but can overfit and be confused by noise. So even if, I think to implement these models and to use Forecaster, you don't need to have a fundamental understanding of the architecture of every single model and how they all work. But I think it's useful to understand the basic differences between them so you can get a better idea of why certain models might work for your data better than others. Now, as I mentioned before, there are multiple different ways that you can train these models as well. And this is kind of independent of what model you choose. It's more so a process of how you split your data, how you provide your data to the model. Um, the two main ways are using a standard train test split and an expanding window. And I'm going to give examples of both of these to make these clearer. But essentially, the train test split, you pick up a small portion of your data at the end of the time series, you exclude it from the rest of your data, you hold it out, and you train your model only on the initial period. Then you have it generate predictions for the time period that your test set covers. That gives you essentially real data that you can directly compare the predictions to, so you can get a good metric of how accurate it is. Um, the expanding window is kind of a slower, more complex version of this, where it repeatedly does training and evaluation on different subsets of data. So to give an example, let's say that this is our data set. This is the counts of like bike riders in Norway from day to day. So this is our training set. You can see we have a clear kind of seasonality here. We have more bike riders in the summer. That's pretty expected. And you can see we kind of cut off this data at a certain point. We have these extra blank time steps at the end. So this is what the model sees. This is the training data. It looks at this, it learns the trends, it learns, about this repeating seasonality, and it we ask it to generate predictions essentially over this last period that we've held out. So then we can take our test set, which is the real data here in green, and we can compare that test set to the predictions that the model generates. And so the predictions might look like this, these red dashed lines. Now, when we zoom out this far, it's a little hard to see. So if we zoom in a bit more to the actual test set and then the predictions themselves, we can analyze it a bit better. And we can see at this scale, there's also a clear, weekly pattern here as well. And we can see that the model really picks up on that and follows this weekly pattern as it makes its predictions. And so this gives us kind of a close-up view where maybe our model works better during certain time periods than it does during others, and we can kind of analyze that. So that's the standard kind of train test split. Now, the advantage of that is that it's pretty quick. You only train your model once on the entire training set, and then you produce your predictions for that test set. The downside of this technique is that sometimes your test set is not super representative of your entire data set. It might include like some random outliers or just changes in trends that aren't really expected. And in that case, your predictions aren't going to work very well. It doesn't mean your model's bad. It just means kind of the data over that period wasn't really what was expected or didn't follow the usual trends that the rest of the data did. So your performance metrics are going to be very, very influenced by kind of the quality of your data over this relatively small period of time. And that can skew your results one way or the other. The way to address that is to use what's called the expanding window technique. So I'm going to zoom into the data a lot in this case. So we start with a essentially very, very small period of time. So you saw in the last example, our training set covered like 3/4 of our entire data set, several years worth of measurements. Here we only have a couple weeks. And we start our model with that couple of weeks, and then we say produce predictions for, the next week, for example. And the model makes its predictions over the next week. Then we can directly compare those predictions to the real data from that week. And we can have the model kind of learn what it did well, what it did wrong. And then that week of data is kind of added into the training set, and the whole model is rerun. It relearns the trends using the new data that it got and using the information from the predictions that it made and how correct or incorrect they were. Then it basically does it again. It makes new predictions for the next week. And this process kind of continues repeatedly, where you keep making these very small scale predictions and then comparing it to the real data. And by the end, you end up with kind of predictions over basically your entire data set. Um, and so the advantage of this is that it's a lot more thorough in evaluation. It rather than, having your performance metrics influenced by a very small period of time, you're running your evaluation over your entire data set. And what you hope to see is that kind of the model gets better and better as it goes. When you initially start and you only have a little bit of data, it probably doesn't work very well, but you hope that it gets better over time. This gives you a much more accurate picture of how well your model's actually learning the trends of the data as it looks at more and more of it. The disadvantages here, it takes a lot longer because you're repeatedly retraining your model, and that takes time. It also kind of makes it harder to calculate like a single number that indicates how well your model works. Obviously, you can average your error across every single prediction, but that might be a little skewed because, as I said, your error is probably going to be kind of bad at the beginning and then get better over time. So it makes it a little hard to like generalize and summarize your model's performance in this case. And as I mentioned, we have LLM assistants to help users understand what they're doing as they go on the web interface. So choosing, what models you should train, what the right parameters are, as well as understanding the performance metrics can be difficult. And so we have this automated LLM assistance provided through the web interface. So for the parameter choices, which I'll show when I demo the site, it will read in kind of summary statistics about your data set, like how big it is, what's the time period, is it daily, is it hourly or yearly, and all of these kind of different summary things to provide very tailored parameter recommendations for your data set. And then once you've trained and evaluated your model, you're looking at all the performance metrics, it will read in that chart of metrics to give explanations about which models are working the best and potentially why. So to show kind of how this works, if we have our web interface here, um, we can click basically the Get Recommendations button, and you can see gives kind of an explanation for a couple different parameters and why it chose those, and it'll automatically fill that in on the site. And again, I think that'll make a little bit more sense when I show the website itself with how that works. Now, just to address some of the limitations of the Forecaster as a tool, because it is, a web interface with a limited number of interactions and buttons, it is not customizable in the same way that, as I mentioned before, like Python would be. Complex customizability always comes at the cost of usability, and we wanted to make this as usable of an interface as possible. And that does come at the cost of being fully customizable. But the way we address that is by making all data and models generated through the site downloadable, so that any users who are interested can kind of continue analysis with their own custom code later on. It also doesn't provide a lot of support for any advanced feature engineering aside from assigning the roles of your columns and filling in missing data. That's kind of all the feature engineering that can be done through the interface. So complex transformations would be something that would need to be done separately. And then there's limitations on data types, and this kind of leads into the future plans for this tool. So we want to increase basically the flexibility of what kinds of data you can use with the forecaster. So right now, it basically requires a static file upload of like a CSV that contains all of your data. And we want to be able to allow it to take in continuous data streams because obviously the nature of time series data is that it continually expands over time. As time increases, you get more measurements, you get more data, and you want to potentially adjust, your models and your predictions based on that. And so we want to be able to read in data from like a database system using kind of a full API to allow for automated updates for your data and for the predictions. So that would allow us to incorporate the forecaster in with like more complex frameworks. So if we took in like a continuous data pipeline, like streams of EICU data, like vital signs from patients, it would allow us to kind of continually retrain and reforecast, every day or every week or however we wanted to do it. And it would read in the new data each time, update the results that are stored in a database, which would allow continually, updated and accurate predictions to be made over time. So that's going to wrap up my slides. I want to walk through a demo of what the site itself looks like, just to ground some of what I've talked about and make it a little bit clearer how you would actually use it. But I want to pause for any general questions first. So if anybody has any questions, let me know now. All right, well, I will stop sharing for just a moment just to pull up the website itself. Let me know if you can't see this, but this is the forecaster. This is what the website looks like. It's available at a URL right now that you can go to. It does require us to create an account for you to actually run jobs. So if after I walk through this, you're thinking that you have, time series data and you'd love to be able to implement it with this to do any kind of exploratory analysis or try things out, you can do that. Feel free to send me an email and let me know what you're interested in, and I will be happy to meet with you if you want, or just grant you access to the tool so we can um, run through an example here of what that looks like to make it a little bit clearer. And so these are, this table is just previous jobs that I've run, and I'll show those in a sec. But let's say that we want to start over from scratch. So we can click Start New Job, and then we just need to upload our file. So I have a CSV file that contains that bike riders data set that I showed you before. So when I upload that and hit Process Data Set, it's going to take us to this page that I mentioned where we assign the columns for our data. So everything will be not included by default, but then we have each of these kind of 6 categories that I mentioned when we were walking through the COVID data set. And you can select, each column to its appropriate category. So we have a date column that can be our time component, the volume of bike riders, that's our target. And then we have, rain and temperature, which we can assign as one of the covariates. So we can assume that, we have forecasts of temperature and rain, so we probably know that into the future a little bit. There's more explanations about what the covariates are down here. So if you forget the differences between those, there's examples in this dropdown. And another thing you can do here is actually plot the data to kind of explore it yourself, to look at potentially relationships between some of your variables. So all you have to do is choose an x-axis, so our date. We'll choose a y-axis, that can be our volume of bike riders. We don't have any grouping column in this data set because we only have the one, region. And we hit generate plot, and now we have a data plot here that shows our data set and shows, the volume of bike riders over time. This is very interactable. You can like draw a box and zoom in. So you can explore specific parts of the data. You can roll over any time point to look at the specific value and date and everything like that. And you can plot multiple variables at once. So if we wanted to like compare the volume to the temperature, we can generate 2 different kind of plots side by side. And we can see, these seem to follow kind of the same overall pattern of increasing in the summer, decreasing in the winter. So with this tool, what we hope is that you can explore the variables in your data set to try to just get a general sense of, what you might want to include, what you might want to leave out, and what you might want to have as kind of different covariates based on how it could be related to the data set itself. So let's say that we've chosen everything, we're happy with this, we can submit our categories, and this takes us to step 3, which is where we configure the training job itself. So this is the page I showed earlier, where you can get the LLM recommendations to fill in some of these parameters. But I'm not going to talk through all of these, but just some of the important ones to highlight. We have a drop down here with each of the models that you can train. So these are the 8 models that I talked about earlier and kind of highlighted the differences between. So they'll all be selected by default. You can train every single model and compare all of them. But if there's only specific ones you want to try, you can do that too. You can define, how big your test set is going to be if you do the standard training testing split. We also have the expanding window evaluation option. These are those 2 different training types that I had mentioned earlier and shown with those graphs. So those each have options, and all of these have tooltips to help explain what each parameter actually means. So there's a lot of different options here. There's more model parameters down here. These are usually pretty good at the defaults, but the LLM recommendations can be very helpful because it kind of depends on particularly the period of your data set, so the natural cycles. So for example, one of these parameters kind of indicates how many previous time steps you want to have the model basically look at once. How big of a window of data is it looking at once? And the right choice for that really depends on, the period of your data set. Where if you have daily data, like our COVID data was, 30 might be a natural choice. You're looking at one full month at a time. If we only had like a monthly data, maybe we want to do 12 because that's the number of months in a year, and we want to look at just 1 year at a time. So there's different kind of intuitive choices depending on your data set and what you want to do. But once you have, all your parameters selected and everything's good, all you do is hit start training job. And essentially what would happen then is that all of these parameters will be saved and they will be sent to a backend machine that we have running that's constantly basically checking a queue. And when you start a job, then a job will be added to that queue. And if there's a free agent, it will pick up that job, it will get the parameters, and it will run it, and it will train all the models, evaluate them, produce your results, everything like that. And so all of that happens kind of on a separate machine. It's not running on your own computer when you pull the website up. It's kind of hidden separately from the website itself, kind of a different piece. And so while that's running, there's a status here that will give you continuous updates as your job is running and training on how many models have been trained so far so that you can get a sense of how long it's going to take. In general, the amount of time that a job takes to run is going to depend on a lot of different factors, obviously, like how big your data set is, how many models you're training. With a relatively small data set like this bike riders data set, which is, just a couple years of daily measurements, you can train all 8 models in a couple minutes. It's not a big time crunch at all. If we had, a huge data set with, hourly data for years and years, and we had different groupings and all kinds of covariates, then maybe we would expect a couple hours for it to fully run. So it just depends on your data set. But I want to show what the results look like so you can get an example of how to interpret kind of the output of each of these models. So I have a previous run here for the same bike riders data set. So under these actions, we can view results. And we can see here in this case a table of a bunch of different performance metrics. I have up here what I just minimized was the results summary generated by when you click the summarize results. This is the LLM assistant I mentioned that gives kind of an overall recap of how well each model worked. And so you can see there's different performance metrics. There's tooltips for each of them to give an explanation for what each of them means. Because if you're not used to time series forecasting, then this probably just looks like a bunch of meaningless acronyms. Um, and that's again, the advantage of having this assistant to help explain the differences between these. There's also values that are both normalized and denormalized. And so the difference between these is that the The normalized values are essentially calculated over a scaled version of your time series. And so you can see that all of these values are, between 0 and 1, essentially. They're all these decimals. Our denormalized values look like these enormous numbers, with, hundreds or thousands of values. And so the uh, the advantage of the normalized is that it's at a consistent scale. So if you had multiple variables or multiple groupings that all are at very different scales from each other, the normalization allows you to really more directly compare the performance across those. So if we had our COVID data set, if we have a bunch of different countries, not every country is obviously going to have similar counts of cases over time. And so an error metric that just indicates, for example, how many cases off was your prediction on average. For a very small country, being off by 100 cases might be really bad. That might be represent a huge difference. That means your prediction was no good. But for like a huge country with a ton of cases, then being off by 100 is maybe really good. It just depends on the scale of your data. Having this normalization means everything's at a consistent scale, so you can compare directly between those different regions. The advantage of the denormalized is that it's at the scale of the data itself, which makes it a lot more interpretable. So, for example, just to pick out one of these metrics, the mean absolute error is literally just the average difference between the prediction and the actual value averaged across all these time steps. And so this is a bit more interpretable because in this case, and we can click on it to sort by it, we can say our best model was off by 753 bike riders on average. And that gives us a really understandable metric of how well the model did. It's a lot more interpretable than a random number of 0.087, which maybe doesn't mean all that much to us. The other thing that you can do on this page is to generate visualizations of your predictions. So all you have to do is click on Generate Visualization for a given model. And if you scroll down, you can look at your predictions. So this example was run with the expanding window. So you can see that we have predictions across almost the entire data set. These are interactable as well. So you can draw a little box and zoom in on a specific time period, so you can see where it works best and where it doesn't. And you can do this for any of the models that you have as well. You can download the models here. You can view an output log to see if there's any errors. And one final functionality here is you can generate more future forecasts. So if I click that, I can define my horizon, which is how many time steps I want to predict for. I can choose my models. I can upload potentially new covariate data, and I can generate new forecasts. So if, our real data here goes until May 2020, I would be able to use that functionality to generate more predictions for the time periods after that as well. And so as we kind of expand out, again, the system for continuously updating data, it would allow you to repeatedly do this over different time periods. So you can continually make updated predictions based on the newest data that you have. So that's kind of a summary of what the results look like here. You can always rerun data sets to make new changes without having to fully re-upload the data or anything like that. You can also view plotting tools, which just lets you generate more plots once you've already run the data. So it works in the exact same way as the plot that I showed before. It just lets you do it at any time, essentially, rather than just on that page. So all of this functionality is kind of available for running forecasting jobs. So I hope that in talking about this, it has maybe spurred some ideas of potential uses that you might have for these kinds of techniques and forecasting models, and maybe have hopefully lowered the barrier for how to implement those techniques and what you need to know and what you need to learn. I hope that some of the things I've talked about can be applied outside of just using Forecaster. But if this is a tool that you're interested in, again, if you have data and you would like to run some exploratory analysis or just want to learn more about the interface itself, feel free to shoot me an email and I'm happy to meet and talk with anyone. But will also be happy to answer any questions that anyone has now.
So if you have a question, please feel free just to unmic yourself and ask.
Aaron, where do you think this would be used in maybe a clinical setting if we had a model to try to predict certain things, either clinical or administrative? Where in a hospital might this be used?
Yeah, I think one of the good examples that I mentioned is kind of continuously monitoring like patient statuses. And so you have a lot of time series data in terms of like measuring vitals of patients. And so by looking at kind of how those can change over time, but across enough patients too, you could have the models kind of learn the signs that might precede, a patient, say, developing sepsis or having some other condition arise. And so being able to forecast what these vitals might look like into the future can be very useful for kind of taking preventative action and trying to provide care to patients as more proactive rather than reactive.
Any other questions? If we have no other questions, we want to thank everyone for joining us today. And if you have other questions, you can reach out to Aaron. I'm sure he would be happy to answer them. And
Absolutely. Thank
we
you.
will see you next month on the second Wednesday.
Thank you.